Alright, so in this video we go over section 4.4 and 4.5 combined, which deals with optimization problems. These are applications of the derivative to determine whether we are going to have a maximum or a minimum, but in this case in the context of an application. And well, the simplest case to illustrate this idea is finding what are the dimensions of a rectangle that give us the maximum area. So this is the idea. For example, we have a we have this rectangle with dimensions x and y, which are really length and width, but we could also have this rectangle like this, x and y, or a perfect square also could be another way to construct a rectangle. However, notice how each of these have a different area. Now, well, do we have the time to look at all the different possibilities and find the area that is the maximum? So no, we don't have that time, but we're going to use calculus to answer this type of questions. Well, so let's see. So, for example, a farmer has 2,400 feet of fencing and wants to use it to fence off a rectangular field. Well, so what are the dimensions of the field that has the largest area? And what is that largest area? So, well, let's see what do we do about this one. So, every time that we deal with an optimization problem, there's essentially two parts of the problem. Number one, there is a calculus part and there is an algebra part. So let's set up the calculus part. And well, the calculus part is the one related to what we want to, in this case, maximize, right? So when we read this word in this kind of word problems, we are supposed to obtain a function that will give us a maximum, you know, maximum, a relative maximum, more in particular, all right? And well, so that's the calculus part, and in this case we want to maximize the area. That is, we will do something like A equals xy. However, here is an issue. The issue here is that this function right here has more than one variable. And well, we need to make sure that we only have one variable. So that's why we have a second piece of information. So notice they're telling us that a farmer has 2,400 feet of fencing. Well, what is that going to be anyway? So, for example, that means that this length plus that length plus that length plus that length will be total of 2,400. Well, in this case, those lengths that I mark with a check mark represent the perimeter of this rectangle, you know, that we could relabel in the following way. We can label them as x, y, x, and y. That is, we have a perimeter that is 2x plus 2y, and in this case, well, the given perimeter, which is the total amount of fencing, is 2,400. 2,400 equals 2x plus 2y. And by the way, this part right here that we are setting up, it's what I usually call the algebra part. So that's the algebra part. And well, so for this part, we're going to use the given information. We use the given information for the algebra part, and we answer the question using the calculus part. So well, in this case, what we're going to do is replace this y right here with using the information that we're given. How come? Well, so what I'm going to do here is to solve for y on the algebra part. That's going to be 2y equals 2400 minus 2x. And dividing both sides by 2, this is y equals 1200 minus x. All right. And then in the end, we're going to go back to this algebra part to answer part of the actual question. Well, so what are we going to do here? So we will substitute this over here on the y calculus. So let's go ahead and do that. So a equals x times 1200 minus x. And well, look at that. That's a function that depends on one single variable. And well, you might want to simplify as much as you can because in order to do the calculus, because if you look at this function the way it is, well, you have the product of two functions, and you might be thinking, oh, should we do the product rule? Well, no, you don't need to do the product rule. Instead, to make things a lot easier, distribute and rewrite this function as x times 1200, that's going to be 1200x, and then x times a negative x squared. Notice I'm writing this in descending order of power so you can see the function that we are getting. So notice how this will make sense with the type of problem or with the conclusion that we are going to get, which is to obtain the maximum. If you observe this this function right here, it's a quadratic function with a negative coefficient. When you have a negative coefficient, that means we have an upside down parabola for which we have a max. All right, that's going to tell us that's a max. However, that's not really the way we are going to justify. We're going to use calculus to justify all this. However, it's good to know somehow what do we have so far so we can compare and we can put things together, so we can in a way predict that we are going to get a max. So let's do the calculus over here. Let's take a prime, which is the derivative, negative 2x plus 1200. And well, what do? We need to find the critical value. The critical value will be the value that will give us, in this case, the maximum, the largest value for the area. So what do? Negative 2x plus 1200 equals to 0. 2x, negative 2x equals to negative 1200. And x equals to 600 feet, by the way. And well, that's the value that potentially will give us a maximum. Well, we still need to, in a way, verify that this will be indeed a maximum. What do? Take the second derivative, a double prime, and that's going to be negative 2. Now, notice that the derivative is less than 0, or it's a negative value. That means that the function is concave down, which means that we have a maximum which checks and agrees with what we're trying to solve. So that means that this value right here of x equals 600 will indeed give us the maximum area. Now, let's go back to the algebra part. So we're going to go to the back to the algebra part to find the missing dimension. 1200 minus 600, that's going to be also 600. All right. So as a final answer, when you do the homework, you need to input your answers in separated by commas or filling in the blanks and boxes or something. So just need to say that the dimensions are 600 feet by 600 feet. All right, and that's final answer pretty much. So this is one example on how do we apply the first derivative and somehow the second derivative test to determine whether we have a maximum or a minimum. and apply it to a context. A very similar situation. So what if in this case you want to create, you want to construct rather um, an area fence in multiple pens. For example, like in this case, we have a zoo that has that needs to fence one snake, six monkeys, and nine cats. However, well, these animals do not get along and they start fighting, so they need to be fenced individually so they don't, so they don't get fight amongst them. So um, but of course, the zoo wants to be fair with all the animals and give them equal areas that are also the maximum area. Now, so the picture here in this case, again, it's going to be very similar to what we did before. So we're going to have an area to maximize, which is x or y, but we need to get rid of this y. Because we need to get rid of this y because we want to work only with a function that depends on one single variable. So that's the calculus part. Let's do the algebra part. Now, in this case, notice how the zoo has available 1,000 feet of fencing. They have 1,000 feet of fencing to fence all this. They're gonna fence 2x's and all these 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 y's in this case. Well, so all this perimeter right here will be to fence 2x's and 17 y's. That is P equals 2x plus 17 y, where the perimeter would be the total amount 1,000 feet. And of course, notice in the previous example, I solved for y in the algebra part, substituted in the calculus part to work with x's. However, you can do it the other way around as well by solving for x and take a derivative in terms of y. It still works. However, just for, I don't know, maybe for traditional reasons, we usually work with x's, solve for y on the algebra part, so we can work only with x's on the calculus part. So let's see, so 17y equals 2x minus 1,000 and so 2x minus 1,000 and divide both sides by y, which is, divide both sides by 17, which is going to give us y equals 2x over 17 minus 1,000 over 17. And what are we going to do? We will substitute this y right here. All right. So that's what we do. Well, actually, yes, that is. No, that's actually the other way around. Never mind. Yep, it's the other way around for whatever reason. So that's 1,000 minus 2x, and this is 1,000 over 17 minus 2x over 17. Well, so let's substitute this over here. The area, which is x times y, which is 1,000 over 17 minus 2x over 17. And of course, you don't want to do the product rule, distribute. So that's going to be 2x squared over 17 and minus, or rather plus, no, this is minus and plus 1,000 over 17x. I know these are crazy numbers, but in the end, it's going to go a lot nicer than it actually looks. All right, so let me have my calculator ready. So we take the derivative a prime, that's going to be negative 4 over 17x plus 1000 over 17. All right, so let's set the derivative equal to 0, negative 4 over 17 x plus 1000 over 17. Set that equal to 0. Let's solve for x. Negative 4x over 17 equals negative 1000 over 17. And let's multiply both sides by negative 17. To get rid of the fractions, the ugly looking fractions, that's going to give us 4x equals 1000, and dividing both sides by 4, we get x equals to 250. All right, 250. So let's see what we're going to get. So is this really going to give us the maximum area? Well, let's find the second derivative to verify that. A double prime, that's going to give us negative 4 over 17. What does that mean? The second derivative is negative, which means we're going to have a concave down function at that value, which means that we have a maximum. Concave down means having a maximum, so this is looking good so far. Well, this is 150 feet. Well, we're good to go and rewrite and find out what the y value is, which in this case is, I'm gonna do 1000. I'm gonna have everything in one single fraction instead to make our calculations a lot easier. So that's gonna be, I'm gonna plug in 250. So 1000 minus 2 times 250, which is 500. 500 divided by 17. Well, that's 500 over 17. 500 over 17. Well, which is approximately 29.4 feet. All right. So that height will be 29.4 feet, and the length of the entire of all the pens combined will be 250. But if we divide this by 7 to find the length and the width of an individual pen, that'll be 250 over 17, and that's 14.7. 14.7 by 29.4, it's going to give us the maximum area of each individual pen. So that means that every single cat, every single monkey, and the snake will have a maximum area of 29.4 by 14.7. All right, let's look at another example. So these are the next one is a very classical problem that involves finding the surface area without actually giving us really the hint that this is the surface area that we have to deal with. So what do we have? We have in this case that a shipping company must design a closed rectangular shipping crate with a square base. All right, that's one of the key words. Square base. The volume is 216 feet cubed. The material for the top, well, in this case, we're going to include the cost. The material for the top and the sides cost $6 per square foot, and the material for the bottom cost $8 per square foot. Find the dimensions of the crate that will minimize the total cost. Well, in this case, well, we want to minimize the cost, but the cost will come from the surface area of the box. Well, let's draw a little picture here. Well, so we have this box. We have this box right here. And well, they're telling us that the base is square because of that. That means the base is also x, but the height is y. Well, so to have a better visual of what's going on in this case, how about uh, we draw this picture in a different way. So suppose we can break this picture apart into all its pieces. That's one. That's the one of the sides. This one is the back. Oops. Well, I'm gonna need more space here. So this will be another side. No. One front, one back, and another top. All right, so that's those are the 6 pieces that actually form this box right here. So notice in this case that the bottom, which is x by x, the top will also be x by x. However, for the sides, all of this will be of the dimension x and y, x and y. You know, well, I don't have space for labeling x and y over here because it's gonna look messy. But you see the picture. These of all these that I circle in orange are the same as the ones that are labeled in orange as well, x by y. All right. Now, so first we will we will set up an expression for the surface area that I will call S. Well, before writing any expressions containing x's and y's, let's be clear with what do we have. So this box contains one top plus 4 sides plus one bottom. All right. Okay, so let's see. So one top, which is what are the dimensions for the area of the top? Well, the dimensions are x by x. So I'm going to multiply 1 times x by x plus plus 4 times the dimensions of the sides, which are x, y, plus another bottom, which is 1 times x times x. Okay, so what are we going to do from here? Well, notice this is an expression for the surface area. Now, we are going to turn this surface area function into a function. Well, let's actually s equals to x squared plus 4x y plus x squared. I know these x squareds right here are like terms, and you might be thinking, oh, let's combine them because they're like terms. No, the reason why we're not going to combine those together is because I will turn this surface area function into a cost function by multiplying the whatever it corresponds for the sides, the cost for the material by whatever value, which in this case, they're telling us that the material for the top and the sides cost $6. So one top and the sides cost $6. That is 6 times x squared plus 6 times 4xy, which is the setup for the sides. And in this case, and the material for the bottom is $8 per square foot. That is $8 times x squared. Now we may combine these together into a single term. That's why we were not supposed to combine these two x's, this one and that one, in the beginning, because we need to make a distinction that one is from the bottom and one is from the top. Well, so let's combine this together. C equals to 6x squared plus 8x squared is that of 14x squared plus 6 times 4, which is 24 x y. All right, so we have a function, we have the calculus part set up already. But we have an issue here. The issue here is that this function has this second variable y that we need to get rid of. So we're going to do the algebra part in order to fix that issue. So the algebra, which is linked to the information that we are given. Now, they're telling us in this case that the volume is to be 216 feet squared. That is, the volume of the box, which length times width times height in our terms is x by y, which is really x squared y. But we know the numerical value of the volume, which in this case is 2016 x squared y. Now in this case, do you want to solve for x, or are we supposed to solve for x, or are we supposed to solve for y? You can do it the way you prefer. However, there's an easier and a better way to go about this. For example, the easiest way here is to solve for y by dividing both sides by x squared. And in this case, well, we're going to get an expression for y, which equals 2016 over x squared. And, well, what we're going to do here, we will substitute for y. All right, so otherwise, if you solve for x, notice you would have to solve a quadratic equation and have a plus or minus, which will take us into trouble, and you don't want to get too many issues with plus or minus. So it's better to work with y than solve for x. I mean, solve for y and substitute for x in the calculus part. So c equals to 14x squared plus 24 x times y, which is 2016 over x squared. Okay, let's simplify this a little bit. Let's multiply this. That's going to give us a big number, but don't worry. In the end, we're going to get really nice numbers. So that's a 14x squared plus 24 times 2016. That's going to give us 48,384. And if we divide x over x squared, so this is what happens with x over x squared. X over x squared, this is x to the 1 minus 2, which is x to the negative 1. So I'm going to write it as x to the negative 1, just so we have it ready to differentiate. All right. C equals to, okay, we're ready to differentiate C prime. So that's a 28 x minus 48,384 x to the negative 2. And well, in this case, well, as opposed to the previous examples in which we were able to see that the cost function, well, the area function was a quadratic function with negative coefficients, we were not, well, in that case, we were able to see that that was an upside down parabola that had a maximum. In this case, it's not just easy to tell such a conclusion by just looking at the function. So we will have to do the second derivative test in order to determine that this indeed will be a minimum, because that's what we want to do this time, minimize the cost, you know. So what are we going to do here? Well, so let's set this derivative equal to 0. So on the one hand, this is the same as 20 c prime equals to 28 x minus 48,384 over x squared. So let's set this derivative equal to 0. That is 28x minus 48,384 divided by x squared equals to 0, and 28x equals 48,384 over x squared. And let's solve this equation for x by cross multiplying with the x's here. So that'll be 28x cubed equals 48,384. Divide both sides by 28 to get x cubed equals to 1728. Okay, so what happened here? We divided both sides by 28, and x equals the cube root of 1728, which indeed x equals, it's a perfect cube, this happens to be 12 feet. All right, is it feet or inches? Let me check again. Yes, it's feet. So 12 feet. All right, so now we need to make sure that indeed, I mean, because if you get this final answer, which is great, we need to make sure that this indeed will be the minimum. And we do that by taking the second derivative. We're going to take it from here because this is the one that is ready to differentiate it using the negative exponent. So c double prime will be 28. The derivative of 28x is 28. And the derivative of this ugly looking expression, negative times a negative, will be a positive 2 times 4800, that's a 96,768 x to the negative 3, which is the same as 28 plus 96,768 over x cubed. All right, now for positive values, because for this type of problems, of geometry problems, we care about positive values. Plug in any positive value for this function, x cubed. So, plug in any positive value. This second derivative will always be positive. What happens when the second derivative is positive? Second derivative is positive means concave down, and therefore we have a minimum, which indeed will be given by this x equals to 12. So now it means that we can go back to our algebra part and substitute y equals to 2016 over 12 squared, and using a calculator for this you should get 14 feet. Now this means that this is going to be 12, 12, 14. So the dimensions, let's clearly state the dimensions. 12 by 12 feet. Oh, let me actually use the units instead. 12 feet by 12 feet by 14 feet. So these are the dimensions that will minimize the cost of building a rectangular box of square base for to hold a volume of 2016 feet cubed, and for which the material for the top and the sides cost $6, while the material for the bottom cost $8. All right. Let's look at one more example, and the next example is very similar to this one that we did in example 3. So how is this going to be very similar? You'll see. So let me copy this picture because I will need it again. Okay, I wanted to just copy this image right here. I want to paste it here on example 4. Okay, looks like I can't just do that. Okay. Let's paste. No, I can't. Control paste. No, it doesn't let me. Perfect. I was able to drag it. All right. Now, a rectangular box is designed so that it has a square base, but in this case, an open top. All right, that is, it has the 4 sides at the bottom, but in this case, it's not gonna have a top. It's gonna be an open box. So what I'm gonna do is just get rid of that top right here. So the volume is to be 2048 centimeters. What is the minimum surface area that such a box can have? So in this case, we're not going to find the minimum cost. We're going to set up a very similar expression that we did in the previous example, but in this case, for finding only the minimum surface. We're not going to go the extra mile this time to find the minimum cost, only the minimum surface area. And well, this minimum surface area will be subject to this given volume, which is the algebra part. That's a volume of 2048 feet cubed. So volume equals x squared y, and 2048 x squared y, where y equals 2048 over x squared. And well, let's in this case set up an expression for the surface area, and that's the calculus part. So what we're going to do here, that's surface area, which is going to be labeled as big S. But before setting up an expression, what do we have? Notice we don't have a top. We have 4 sides and 1 bottom. All right, so let's set up the expression for the sides. So for the sides, in the same way that we did it in the previous part, 1 times x times x, that's going to be for each of this. So in this case, big S equals 4xy, or rather, I'm going to write the x squared first, just so I can have the y's in the end and do the substitution there. So that's going to be this 1 times x is going to be x squared plus 4xy. Well, in this case, we're going to substitute this 2048 over here to come up with a function of a single variable. So s equals to x squared plus 4x times y, which is 2048 over x squared. So let's multiply this, let's simplify that. So 2048 times 4, that's going to give us 8192. in just the same way x to the negative 1, because x over x squared is x to the negative 1. And we're going to leave it in this format so we can have it ready to differentiate it instead of having the x to the positive 1 in the denominator. S prime, that's the derivative 2x plus, or rather minus, well, let me make this x look like an actual x. Sometimes it doesn't work. So 2x plus, or not plus, actually minus 8192 x to the negative 1, or rather negative 2. We subtract 1 to the exponent, and well, let's set the derivative equal to 0. To solve for x. So, well, actually, let me rewrite this. 2x minus 8192 over x squared with positive exponents. Okay, for whatever reason, I always struggle to change pencils here. Okay, so 2x equals to 8192 over x squared, cross multiply to get to x cubed equals 8192. Or x cubed equals, divide both sides by 2 to get 4096. And x will be the cube root of 4096, which in this case it's going to be another perfect cube, that is 16. Well, so we have the dimension x. Now let's of course determine or show that this will be indeed a max, or rather a minimum. So that's s double prime, that's a 2 plus 8192 times 2. That's going to be a big number. 8192 times 2, that's a 16384. X to the negative 3, and I'm going to rewrite this 2 plus 16384 over x to the third power. And again, this will always be positive for positive values of x. That means the second derivative is positive, concave up, giving us a minimum. So this dimension will be, feet by the way, will be the minimum. So what are we going to have? Go back to the algebra part. 2048 divided by 16. Was that a 16? Yes, 16 squared using a calculator should give us 8 feet. So this means that this open box will be of dimensions 16 by 16 by 8. I know the picture is giving us like a larger height, but I mean the numbers are actually telling us something else. Okay, so dimensions are 16 by 16 by 16, and by 8 rather. Oh, and let me also have the units. And well, so the box is actually going to look more like this. You know, more like a flatter box but a wider bottom. And well, these were a few examples on solving optimization problems for this section. So this is a good place to quit the video. I'll see you in the next section.